Well, hello, calculus students and seekers of general truths. We finished the last video on this note here when we estimated the error when we figured out the error when estimating the cosine of 1/2 using 4 non-zero terms. And so let's talk about some of the terminology, because you're going to see this in different textbooks, in different contexts. This is Taylor's theorem, as I have written it here. And again, we don't know much about this point A. We hardly ever know what it is. But what we can do is we can say, what's the maximum of that point, right? What's the maximum of the k plus first derivative of f at that point A? What's the biggest it could possibly be? Whatever that is, once we figure out that max, we can flip this equal sign to a greater than or equal sign. And then we can say that this error term right here is greater than this difference between the exact answer and the approximation. So it's another way of saying the estimation using a finite series or finite polynomial is at most this error term. Okay. We know this as Taylor's theorem. It is also called the Lagrange error bound, and this is the term that you will hear more often. A little, mathematical history is a little bit complicated. Taylor was working on this problem. There was another mathematician named Louis Lagrange, and Lagrange proved a more rigorous and a more complete version of this theorem, although Taylor did quite a bit of the work as well. So it's a little bit mixed as to who gets credit for this. Taylor obviously has his Taylor polynomials, and he has this theorem named after him. But when we talk about putting a limit on the bound here, it is named after Louis Lagrange. So for more on that, you can see some of the notes and some of the description here in the video to look at some of the mathematical history. But I want you to take away the name of this type of error bound. It's called the Lagrange error bound. The theorem is Taylor's theorem. Okay. So now, with that in mind, let's return to our big three questions. We talked about how do we make a series approximate a function. We do that with the Powell series, Taylor series, Maclaurin series. Does the series converge? We have a bunch of tests. Okay? And then we talked about how close is the approximation. Well, we answered that over the last couple videos with alternating series error bound and the Lagrange error bound. Now, the final question here is an exact answer possible? Okay, is that possible? So let's extend this idea and let's just use cosine. It always helps when we can apply this to a well-known function. Okay, so this is Taylor's theorem right here, and we're using f of x as cosine. Okay. Well, remember that when k was equal to 6, the sixth degree polynomial, we had the error come out to this. Okay, just a quick reminder. This is the calculation for that error, right? When we had, when k was equal to 6, this is the error that the limit of on the error, the upper bound on the error that we had for this. Okay, so that was the error. The difference between the exact answer and the real answer is at most this small number. Okay, and then we said, well, do you want using a 6th degree polynomial, we came within 1.55 times 10 to the negative 6, and we want more precision, use a higher degree polynomial. So let's kick it up a few notches and use a really high degree, as high of a degree as we can. What if we took this error bound here and try to calculate it using the limit as k approaches infinity, right? So this is like saying, if I replace a k with infinity here, this would be my error bound. Okay, so what happens to that error bound as we use more and more terms, or as the number of terms in the polynomial approaches infinity? Another way of saying that is as the power of the polynomial increases towards infinity, what happens to our error? Well, you see here that the k plus first derivative of a, or at some point a, is at most 1, right? So this limit on the left is less than or equal to this limit on the right, just taking out this k plus first term, or the k plus first derivative at a. Why? Why is it 1? Well, because of the particular function that we're working with here. F of x is equal to cosine of x. Any derivative then is either sine with a positive or negative, or cosine with a positive or negative. And both sine and cosine are bounded between -1 and 1. So we know that this limit on the left here, and this is again the error or the remainder, right? The limit on the left is at most equal to what's on the right here. And if you look at this function, well, you can see that the top of this numerator, the top of this fraction, the numerator, is a polynomial. It's something k plus 1. The denominator is a factorial function, which grows much, much, much faster than the top. We could use some rigorous algebra tests to figure this out, and I can show you in a separate video, but without getting off topic, the intuition here is that the denominator is going to grow much faster than the numerator. So as k gets very, very large, this limit goes to 0. Okay? And this is a profound thing, because if the error here, right, if the error approaches 0 as k approaches infinity, and k is the degree, and it also affects the number of terms, right? If the limit of the error approaches 0, that means, well, what does it mean? That means that cosine isn't just approximately equal to the infinite series. Remember, this is the Maclaurin series for cosine. But that cosine is in fact exactly equal to the series. In other words, let's go back. As the power of the polynomial, or as the number of terms approaches infinity, the error goes down to 0. So, once again, this approximation, we can say it goes away, and in the long run, if we could calculate this series to infinity, we would get the exact answer. And so this is somewhat of a groundbreaking result that shows that we could not just estimate, but arrive at an exact answer for the cosine of any number, or of any number we want, using its Maclaurin series or its Taylor series representation. All right, so take a moment, let that sink in a little bit. Jot down your questions and prepare to ask them. Feel free to comment and to ask as many as you need to ask. Okay? And then I'm going to conclude this video with a comparison of the alternating series error bound and the Lagrange error bound. So we have two methods here of finding error of infinite series, or finding the remainder of infinite series. So let's compare them. Well, if you want to use the alternating series error bound, it's a little bit easier to calculate, I think, but the series must be alternating. So that's one very big caveat. And it uses non-zero terms. So I refer you to the previous several videos where, using the alternating series error bound, we just look at the non-zero terms. For the Lagrange error bound, we need to find the upper bound of that mystical point C, or A, that k plus first derivative at some point A, right? So that might be a little bit trickier. It's not as easy to calculate as the alternating series error bound. But it doesn't have to be alternating. The Lagrange error bound works for any convergent Taylor series. And then finally, another big distinction is that the Lagrange error bound uses the degree of the polynomial, not the number of terms necessarily. Sometimes we get caught up because we equate the number of terms with the number of non-zero terms, but the Lagrange error bound, you really have to think about it in terms of the degree of the polynomial. Okay? All right, so hopefully these two error bound methods is enough for you to do some really serious calculation, and hopefully this entire series of videos enlightens you quite a bit about how calculators really work, how do we actually compute complicated numbers, how do we work through how we actually compute results of complicated functions. As always, please ask for help when you need it. Keep thinking really hard about these important questions. Keep seeking truth, and have a wonderful day.